Hi, sorry. Jordan is here.
Hi, can you hear me?
Yeah.
Cool.
Yeah, it's strange. This time you joined with no problem, right?
Yeah, because I did full preparation. We are waiting for you.
Yeah, Junwei is here.
Yeah, great. So it seems that you registered my account using my Princeton email.
Yeah.
Yeah. Okay.
Let me double check.
Yeah, I think you told me that.
I registered one for sure. Let me check which one. Yeah, Princeton one, ZY6.
Yeah, ZY6. Yeah.
Maybe last time you logged in by your Google account.
Yeah, maybe.
Yeah. So, please keep an eye on the attendees, just in case Professor Robbins is not registered successfully. I can manually promote him to panelist. Yeah.
Yes. Yeah.
Yeah, he confirmed yesterday he will join around 2:45.
Yes.
Yeah. Junwei, you got some weight.
Cannot get exercises.
Seriously.
So have you guys started the fall semester?
Yeah.
Yeah.
Yeah, same here.
Jordan, are you TA this semester?
No, I'm funded by fellowship.
Oh, yeah, I remember. Junwei, can you send a reminder just to say that we have opened the Zoom?
Okay.
Yeah.
Jamie said in 1 minute.
Okay, great. Junwei, do you have his cell phone number?
So has he confirmed?
He has confirmed.
Yeah, he confirmed just a few minutes ago saying that he has some internet problem. So
okay.
I'm wondering if he is confused by the Zoom setting that he needs to click join as an attendee. Oh, yes, works. Hello, Professor Robbins.
Hi, Professor Robbins.
You hear me?
Yes.
Yeah, yes.
Okay.
Great. So we have, I'm having some technical problems, which I always do. So can I take about 2 more minutes to try to improve something?
Sure.
Okay.
So your voice is a little bit low. Can you move closer to the microphone?
Oh, wait, you want me closer to the microphone? Can you hear me?
Yeah, your voice volume is a little bit lower than it should be.
Oh dear.
But it's clear, yeah.
Yeah, let me, okay, I'm going to try to put this on my iPad, maybe. Let's see if I succeed. Oh, man. Okay, so I'm still too low. Let me see what I can do with the microphone.
I think it's better now.
Yeah,
Right?
It's better. When we closer to the microphone, it sounds better.
All right.
Now it sounds clear.
Okay.
Loud and clear.
Yeah.
Okay.
Can you share your slides?
Yeah. That's what I was doing before. I see what's happened to them. Hold on. This is so weird. Okay, so I'll go here. I have to get it back from the iPad. Okay, now I have to get this back from the iPad, which is I'm having trouble doing for some reason. Okay, let me try something else. So bad. Okay, how can I could turn this off. Let me try turning this off. Okay, if I'm having trouble. It's on my iPad, and my iPad's stuck, and I can't turn it off. Let me think. I have an idea what to do. I'm gonna close Adobe. Force quit Adobe. Yeah, open it again. Okay. And I'm going to pray this works. Okay, now I'm going to share my screen. I'm almost there.
No worry, no worry.
Yeah, take your time.
Can't share it. Okay.
Yeah.
Do you see anything? Am I sharing at all now?
No.
No.
Not at all.
Yeah. Think easier. You just click the green button, the share screen, and share.
That's what I did.
Yeah.
Let me do it again.
Yeah.
Try it again.
So then you get to choose which window you share.
Yeah, I know. I'm having trouble with that. Okay, now I've lost you completely. How do I share this? Okay, so I can hear you, but I can't see you at this point. So I have the wrong window. I'll tell you what, I'm going to, maybe I can get off. I'm going to stop Zoom and start it again.
Sure.
I'll you all over again because there's something gone wrong.
You just restart the Zoom. Maybe
yeah.
Problem.
Okay. Okay. It's not working. Can you still hear me?
Yeah.
So I didn't get off. Even though I stopped Zoom.
Mm-hmm.
Oh, I see now. I seem to have two Zooms.
Actually, so do you have another account so we can make both your accounts as a panelist, so you can open both your iPad and computer? Oh. I think we lost him, right?
Yeah, I think he logged off.
Yeah, okay, okay. Just wait for 1 minute.
Mm-hmm.
Yeah, he is re-logging to rejoin.
Now, let me see if my screen will share.
Yeah. So, or if you don't mind, you can send your slides to me and I can share, but I will just.
Okay.
Yeah.
He can let you to remote control him.
Yeah.
Okay. I will do that. Okay, I sent you something.
So now it should arrive in 1 minute.
Yeah, I've received it.
Okay.
I can play it too.
Yeah, Junwei, maybe you can share. Yeah.
Okay.
And later, Jamie,
let's try.
Remote control. Yeah.
I'm sorry. This is,
No problem.
things all wrong. That's never.
It happens.
First time on Zoom that this ever happened. I couldn't. It won't work. Okay, so you're going to share, and I'm just going to use your share.
Yeah.
Okay.
Am I sharing the right one?
No.
I've even infected you.
No, sorry. I have a few to see.
Maybe could I still be? Is it? I'm still sharing? No. That be it? It looks like I'm still sharing somehow.
Yeah, now it's
Now it's sharing.
Yeah, yeah. Go full screen. Yeah. Let's start.
Okay.
Yeah.
So can you try the remote control?
Maybe it's too late. Just let Junwei control the slides.
Where is the remote control? I've never used that.
Yeah.
Maybe you can just tell Junwei to turn the pages.
Yeah.
Yeah.
Let's do this. Jamie, whenever you want to turn to the next slide, just turn next slide. Junwei will do that.
Okay.
Yes. So we will not interrupt you during the talk, and we will gather all the questions raised during the talk raised in the QA section all together, and I will ask those questions to you after the talk. We will have a small Q&A section.
Okay. So now that I've used up all this time, how long do I have left?
So it's about 15 minutes. It's all up to you. So whenever you feel comfortable, you can stop.
So Jordan, let's start. Yeah.
Okay. Hi everyone. Welcome to the online seminar on mathematical foundations of data science. Sorry for keeping you waiting, and thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great pleasure to introduce our distinguished speaker, Professor James Robbins from Harvard. Professor Robbins is currently the Mitchell and Robin LaFolley Dunn Professor of Epidemiology at Harvard Chan School of Public Health. He is an epidemiologist and biostatistician. He has made fundamental contributions to causal inference and dynamic treatment regimes, and has influenced many generations of researchers. He is best known for advancing methods for drawing causal inferences from complex observational studies and randomized trials, particularly those in which the treatment varies with time. He introduced a novel framework for drawing causal inference from observational data in 1986, and he has developed many famous models and methods such as G-formula and G-estimation of structural nested models, marginal structural models, W-robust estimators, and high-order influence functions for statistical functional estimation. He is a 2013 recipient of the Nathan Mantle Award for lifetime achievement in statistics and epidemiology. The title of his talk today is On the Impossibility of Assumption-Free Inference for Causal Effects Estimated by Machine Learning. Please join me in welcoming him.
Thanks for inviting me, and I apologize for all the technical problems that I caused, which is not unusual for me. Okay, so how do we do this now? I guess, is there a way, do I have to ask you to change the slides, or?
Yeah, when you set the next slides, I can click.
Next slide. Okay, so the work I'm going to describe today is joint with my postdoc Wen Wu and my colleague Rajarshi Mukherjee. It uses a lot of material from earlier papers on higher order influence functions with Ott van der Vaart, Wen, Rajarshi, Eric Chechen, Whitney Newey, and Ling Li. All right, let's start. Okay, so valid inference, i.e. valid tests and confidence intervals for causal effects, are important in many subject areas. Since I'm in medicine, I'll discuss that. In medicine, it's critical to evaluate whether a non-null treatment effect estimate could differ from 0 simply because of sampling variability. So you get an estimate of a treatment effect, and you want to, but if it's really consistent with 0, you want to know that. And that's especially true if the treatment estimate looks like the treatment's beneficial, but it has side effects, toxicities. So you don't want to give it to people unless it really is beneficial. And for that, you better know whether it's really different from 0 or the data is consistent with 0 because of sampling variability. Conversely, when a null treatment effect estimate, let's say you're right near the null, but I'd like to know, is it compatible with a clinically important effect that I just failed to discover because the sample size wasn't larger? That is, if my confidence interval includes a clinically important effect, I would, and 0, I would want to get larger number of subjects. Okay, so in observational studies, control of confounding is a necessary condition for valid inference, valid causal inference. And I'm going to explain that causal effects are not consistently estimable without assumptions, which are usually smoothness or sparsity assumptions on the propensity score or the outcome regression. This is true even when the causal effects are identified. That is, even when they're identified from the joint distribution of the observed data, you can never reject the hypothesis that the bias of your estimator might be order 1. Okay, let's go on. This can all be clear to you. So if that's true, if the bias could always be order 1, then from my point of view, if I don't want to make any untestable assumptions, all the people who estimate causal effects and give confidence intervals are in a diluted world, because no matter what they give you as a point in estimated confidence interval, they could be off by order 1, no matter how large the sample size is. You're going to see why this is later. And so their justification is always something like, at the extreme of parametric model, at the other end, sparsity or smoothness or something, or well approximated by a neural net, these regression functions. Okay, so I might end my talk there, because in that sense, I have nothing positive to add. And most of our parents taught us, if you don't have something positive to add, don't go criticizing others. So I should shut up. However, there's another curmudgeon social norm, that if you have nothing positive to say, that does not relieve you of your duty to criticize others. And that's what essentially the talk's about today. That somebody, imagine you read a paper and somebody gives a point estimate and a confidence interval for a causal effect. There's no unmeasured confounding, so it's really identified if I had an infinite sample size. And they say the confidence interval covers 95% of the time. And if I just say to them, well, maybe not, because the bias could always be really large, they'll say, well, it could be, but I believe my, let's say sparsity assumption. So what I'm interested in is empirically proving to them that they're wrong, okay? So I want to come up with empirical tests that state-of-the-art confidence intervals fail to cover. Okay, that's my goal. Okay, there are going to be a lot of new notions. I will get to them while we're going along. I think I'm going to ignore going through them here. I'll explain them when I get to them. But my final goal is when somebody reports a confidence interval and says it has 95% coverage, I want a method that puts an upper bound on the actual coverage rate of that interval without making any smoothness, or I'm not going to make any smoothness or sparsity assumptions, any assumptions about the regularity of the propensity score or the outcome regression. But I'm still going to tell them possibly that they don't have, their 95% interval can't cover more than 10% of the time with confidence, 95%. Okay, so that's my goal. Okay, go on. I'm going to get to these as we go on. I'll skip this slide. Okay, keep going. Okay, keep going. Keep going. Okay, so I'm going to put this in context of an actual data, so it's not abstract. So I imagine I have a treatment A, an outcome Y, and high dimensional covariates X. And I have 10,000 up to 100 million people in my study. A is going to be binary, the treatment. And X is, as I said, d-dimensional. Y can be binary continuous. The dimension of X could be large. And I'm going to regard these as IID samples, and I'm interested in causal effects. Okay, let's go ahead. Okay, we have observed observational data, but we're going to correctly assume, quotes, nature ran a randomized trial given X. That is, we're going to assume that there are no unmeasured confounders. In X is if I could perfectly control for this high dimensional X, I could get the causal effect. In that case, effectively, the only difference between a true human run randomized trial, given that I've made this assumption, this untestable assumption, is we do not know the probability of treatment given X. The probability of treatment given X is also called the propensity score. And you can see it's the probability A equal 1 given X equal X, or the mean of A given X equal X. And I'm going to use, for the propensity function, I'm going to use pi of X. It's only going to be two symbols you have to remember. One is pi of X, that's propensity score. Okay, next slide. Okay, and I'm going to assume, as usual, we have what's called positivity. Pi of X is bounded away from 0 and 1. Nobody gets, no level of X gets treatment or no treatment with certainty. Then under that, with no confounding and positivity, association is causation, and also with things like no interference between treatments. And in fact, the causal effect of treatment at level X, that is identified by the mean of Y given A equal 1, X equal X, minus the mean of Y given A equals 0 and X equal X. So in other words, I've made enough assumptions to turn this into just a statistical problem about the observed data, okay? Okay, if A is binary and the treatment effect is the same at every level of X, then you can see that the treatment gamma of X, that's the treatment effect among people who have level X of the covariates, I'm going to assume is constant. I don't, these are all things only to get, I'm trying to get to a statistical problem. So it's not important, the assumptions I make about causal inference, but I'm just showing you it's connected. Then in that case, the average treatment effect, the functional, that I'm trying to estimate is the that numerator over that denominator, where I'm going to use B of X. This is the only other thing you have to remember, is the regression of Y given X, not the regression of Y given X in treatment, just the regression of Y given X. So the numerator is the expected conditional covariance of Y and A given X. That's the definition of that. And the denominator is the expected conditional variance of A given X. So that's under my assumptions, that's the statistical functional I want to estimate. And I want a confidence interval for it. And everything else about causality now you could ignore. The result, I've chosen this functional for reasons I'll explain later, but this is, the results I'm going to give are generalized to a large class of what are called doubly robust functionals with something called the mixed bias property of Andrea, of Rotnitsky, Smucker, and myself. And, but I'm not going to get into all those other functionals my results apply to, because I'm going to try to make everything easy except for the philosophy. Okay, let's go ahead. Okay, so those are the two functions you have to remember. The mean of Y given X, B, mean of A given X, pi. Okay, so I'm going to concentrate on, so I have a numerator over denominator. I'm going to concentrate on estimating the numerator for now, because it's going to be, estimating the denominator is going to be equally easy. Okay, so notice psi is 0 under the null hypothesis that Y and A are independent given X. So psi equals 0 means that A has no effect on, no causal effect on Y within levels of X, any level of X. Okay, so how would we estimate psi? Well, anybody would estimate, would just plug in estimates in the definition of the functional b hat and pi hat for pi and b. So that's what I'm going to call our estimator. I'm going to call it psi hat doubly robust. Okay, this plug-in estimator actually turns out to be an estimator based on the influence function of that functional. Because the first order influence function, that functional, you don't have to understand what that means right now, but is just the random variable quantity y minus bx times quantity a minus pi x. So this is a natural plug-in estimator, and this is also the state-of-the-art estimator. This is what people are using. Okay, let's continue. So this estimator has some bias. What is the bias? Well, if b hat and pi hat are non-random, that is, I haven't estimated them from the same data as from the estimator, then if you just do algebra, the bias is b minus b hat, the mean of the function b minus b hat times pi minus pi hat. That's pretty intuitive. And so we call this a doubly robust functional, because if you're lucky enough to have b hat equals b or pi hat equals pi, you get no bias. You're unbiased. It's actually unbiased for the expected conditional covariance psi. So you only need one to be correct. And also because of the product form, go back for 1 second, because the product form, if both of them are close, you get a very small bias because you multiply two small numbers. Okay, so that's why we call it a doubly robust functional estimator. Okay, so the use of doubly robust functionals, or another of this estimator, there are other doubly robust functionals, is fundamental to obtaining valid confidence intervals when using machine learning estimators to estimate pi and b, where the machine learning estimators may be, in the statistical sense, black boxes, because no one's worked out why they work. Like, deep neural nets, everybody's working on it, but for the moment, really, it just returns an estimator. And certainly no one knows its properties if we don't assume smoothness or sparsity or something. Okay, so I'm going to just treat the estimates of pi and b as a black box. So why is this true? Let's go ahead. Well, except for special estimators, only doubly robust estimators have second order bias. Other ones have bias like just the mean of b minus b hat to plug in or something like that. And to have a valid confidence, so the standard, so just to get to it, what I'm actually going to do here is I'm going to use estimators where you split the sample, and I'm going to estimate the Nuisance functions, b hat and pi hat, from 1/2, and then use my estimator I showed you based on the other half of the sample. And I'm going to condition on the half of the sample where I estimated b and pi. So I think of the data I have as the sum of IID random variables, and b hat and pi hat is fixed, okay? And so because b and pi are high dimensional, b of x and pi of x are high dimensional non-parametric regressions, they can't be estimated at n to the minus 1/2, okay? But they might be estimable like both at n to the minus 1/4, in which case, because we have this product bias, we have a hope of having bias of n to the minus 1/2 or less. And recalling that the standard error is going to be 1 over the square root of n to the minus 1/2, because I'm viewing the data I'm actually using the estimator is the sum of IID random variables. It's the sample average of y minus b hat x, a minus p hat x, and I'm assuming b hat and pi hat, I'm conditioning on them because they're from another sample. Okay, So most estimators don't have second order bias, and therefore they could never have standard error less than, have their bias less than their standard error of 1 over the square root of n. And therefore, walled confidence intervals centered on them won't have correct coverage, because a walled interval has to have, of an estimator, only has correct coverage if the bias of the estimator over the standard error is near 0. Okay, so that's why we have to use doubly robust estimators to get bias that may be small. Okay, let's go on. Okay. And the reason we use machine learning algorithms here is they may be better at estimating those unknown expectations than parametric models, ordinary kernel smoothing using high-ordered polynomials when the sample size is large. It does good at estimating regression functions. And that's why people are using them. Okay, in this setting. Let's go on. Okay. So my point is that pi hat x and b hat x have unknown statistical properties in general. So could we ever still get valid tests and confidence intervals? Especially if we do not want to wish to make unverifiable smoothness or sparsity assumptions. This is the main issue in the talk. Let's continue. Okay, the second key idea, which I've already mentioned, after double robustness, that is using an estimator that has second order bias of b minus the expected value, b minus b hat, pi minus pi hat, is sample splitting, which I already mentioned. Go ahead. We have to estimate sample splitting to estimate the nuisance regressions to construct, if we're hoping to construct efficient asymptotically consistently asymptotically normal estimators, because we have to avoid problems with correlations between our estimator b hat x and the data that we're performing our estimate on. And you can only deal with them if they're from the same sample. The only way in general we know to deal with them is if they're Donsker. And we don't know that these complicated black box machine learning programs are Donsker often, that they're okay. So now I'm going to tell you the state of the art. We have the background. Here's the state of the art algorithm. I'm going to tell you how to, 2 estimators. I'm going to call one psi hat doubly robust and psi hat cross-fit. So what do? We split the end study subjects into 2 parts. One we'll call the estimation sample of size n, and a training sample of size n training, which we'll take for simplicity to be of the same size to be half the data. So we estimate b hat x and pi hat x from the training sample using ML methods. Then we go to the other half of the sample, the estimation sample, and we compute psi hat dr, which I showed you before. And psi hat CF is the estimator where I average psi hat dr with its sister, which I'm calling psi hat bar dr, that exchanges who's the estimation sample, who's the validation sample, and I take the average. Okay, that's trying to recover the information I lost from not using half the data before. Okay, so the following theorem gives the standard asymptotic properties, this is well known, of psi hat dr, conditional on the training sample. Well, given the training sample, it's asymptotically normal because it's a sum of IID random variables. So it has standard error 1 over the square root of n of that order. And its bias, I already told you, but that's its conditional bias because I'm treating b hat and pi hat as fixed functions. So I put condition TR, means conditional on the training sample, because b hat and pi hat are, the function b hat and pi hat are fixed functions given the training sample. So writing out what I actually mean is that's the conditional bias, that integral, where f of x is density of x. Okay, so that's okay. Now, and so notice the expectation there is only random for the training sample. okay, let's go on. And so that being OP n to the minus, if that the bias is OP n to the minus half, then the conditional bias is going to become negligible compared to the standard error. And that's going to allow valid confidence intervals. Okay, this won't generally be true if the bias is in second order, as I explained before, because you can't estimate bx minus b hat x as at an n to the minus half rate. Okay, so what about unconditional results? So if the conditional bias is order and probability n to the minus half, for now I'm talking about the probability in the training sample, because I've integrated over the estimation sample, because that's the conditional bias, and b hat and pi hat converge to the true Gaussian mean square, then n to the 1/2 psi hat dr minus psi converges both conditionally and unconditionally to normal distribution with mean 0. Furthermore, n to the half, remember big N is the total sample, little n is half of it, n to the half psi hat cross fit minus psi converges unconditionally to a normal distribution with mean 0 in variance equal to the semi-parametric variance bound. That is, cross-fitting recovers all the information provided the conditional bias is OP n to the minus 1/2. It's B is pretty trivial. I mean, no one worries about B. It's A that drives everything. You need A to be true for these unconditional results to hold. So, and for the, okay, go ahead. And you need it to be true for the walled intervals. The estimator plus or minus the 1 minus alpha interval Z, the Z alpha over 2 being the normal quantile, times the estimate of the standard error, or the similar version with crossfit, to be 1 minus alpha asymptotic confidence intervals for psi. Okay, but that all requires that the bias is small o n to the minus 1/2. Now, though this is a standard result, it's of essentially no interest to us, because without smoothness or sparsity assumptions on V and pi that might not hold, we can never guarantee the bias is OP n to the minus 1/2. How do we know what the bias is? Less important, and historically, even if we had smoothness sparsity assumptions, often V hat and pi hat, we don't know their statistical properties if they're machine learning black box estimators. So what we're interested in is an assumption-free inference, no smoothness or sparsity assumptions, unlike in the usual literature. But if you say essentially nothing, consistent estimation is not possible, because I can't control the bias. Go ahead, without those. That was the logic of a paper with Ritov and I on something called cursive dimensionality appropriate asymptotics or something. So we can never empirically test that the bias is OP n to the minus 1/2. And thus the hypothesis, we can never test the hypothesis that n to the 1/2 psi at dr minus psi is asymptotically normal. But what are we interested in? Okay, that's all true. But what's the interest in this paper? We're interested in real studies. That is, we're interested in questions like, at the finite sample size n, is the actual coverage under the law generating the data of the interval that was reported in the paper, let's say that, less than a fraction? Like, I'm interested in if I can say empirically that the actual coverage of that nominal interval is less than 0.2 of what its nominal coverage is supposed to be. Okay, that's the kind of statement I want to make. And notice that statement is only talking about the coverage of somebody's interval. It's an interlocutor relationship. I'm criticizing someone else. You say it's 95%. No, I'm going to prove to you it's only 10%. Okay, that's all I can hope to do. Okay, let's go on. So, so since we want assumption-free inference, we're going to regard the training samples fixed. And so usually for us, there's going to be some exceptions. The only randomness is the estimation sample. And therefore, our inferences are going to rely on being in asymptopia, only if posit that at our sample size of n, the quantiles of the finite sample distribution of psi hat dr minus its mean, conditional on but just psi hat dr, because we're conditioning on the training sample, that since that's the sum of IID random variables, we have a large enough sample size that it's close to a normal. But and we can estimate standard errors with the bootstrapping the estimation sample. We could do completely finite sample stuff if we use finite sample inequalities instead of normality. Okay, let's go on. Okay, so that discussion, let's go on, leads to the following question. Can tests be developed that have the ability to detect whether the bias of a DRL estimator that I'm given in a study is the same or greater order than a standard error? So the nominal 1 minus alpha confidence intervals reported under cover. If yes, can we construct new estimators that are generally less biased? And can we do this without refitting, modifying, or even having knowledge of the ML algorithms that are employed? And without essentially requiring any assumptions at all, aside from a few standard, quite weak assumptions, in particular, without making smoothness or sparsity assumptions, making no assumptions about the function class that the propensity score outcome regression live in, that is. Okay, the game I'm going to play is you're going to give me your data, or at least the half of the data you use to compute your confidence interval, plus I don't care about the training sample. You just give me your B hat and your pi hat, whatever you got, whatever regression function for y given x and y given x that you got. So you've given me the data from the estimation sample, the new regression functions you plugged in, and I'm going to try to tell you your inference is invalid, if I can. If I can't, I'll say, you'll see, I'll say, I don't know. I can never prove it's valid because I never know what the bias is, the true bias is. Okay, let's go on. I'm going to show you the answer to these questions is sometimes yes, by using high order influence functions and tests and estimators. And the key idea is I'm going to estimate part of the conditional bias. So the conditional bias can always be order 1, and I could never know it without assumptions. So I'm going to estimate part of it, and I'm going to use a second order U statistic, which we call a second order influence function, to estimate part of that bias. Okay, and IF22 is going to depend on a number of things. It's going to, when you see it, it's going to depend on an index K, which is going to depend on a vector of covariates, a basis, K basis function, ZK, that I am going to choose, me who's trying to disprove your confidence interval, chosen from some big dictionary of functions of X. And the bias, and I'm going to not say much about how I'm going to choose those, but I'll show you why it's important to choose them well and what's possible. In our bias-corrected estimators, I'm just going to take your estimator and subtract off the statistic, because the statistic is an unbiased estimator of at least part of the bias. So I'm hoping the bias is less. Okay, continue. Okay. So as I said, the statistic I'm going to add, this part bias correcting statistics is a second order U statistic, depends on the choice of K basis functions. I'm going to use overbars for vectors of the high dimensional covariates. And I'm going to let, whatever that is, which signal was that, omega inverse be the inverse outer product matrix of the of my vector of basis functions. I'm also going to let the empirical estimate of that be, I'm going to put a hat on that. And I could just use the empirical estimator. I could use some fancy estimator of the inverse of the covariance matrix. In this talk, I'm going to, because there's so many things to cover, I'm going to assume we have semi-supervised data. That's data where you have unlimited number of covariates X. You have a sample size of 1 trillion on X, but you have a smaller sample size, let's say of 100,000 or 1 million on A and Y. That's called semi-supervised data. That's going to allow me to treat the covariance matrix, really the outer product matrix, I'll call it the covariance, as known. So I'm going to, because I don't have enough time, I'm going to completely ignore the question of whether, how to do all this when you have to estimate the covariance matrix. Okay. Secondly, go back one slide. Secondly, the bigger K is, in general, the better it is, because I want, because that means the bigger K is, the more basis functions I use, the larger the part of the total bias that I'm estimating. But if I was doing estimates of, I'm going to choose K less than N here. If you're estimating the inverse covariance matrix, and you're not going to assume sparsity on it, you don't really have any choice but to use the empirical. So you need K less than N to invert the empirical covariance matrix. Furthermore, if K is less than N, I'm going to have, we'll see later, I'm going to have surprising power to detect certain things. Go ahead. I think I talk about it here. Yeah, so the stuff about simulate, let's see. So don't worry about the simulations are about when I'm estimating the covariance matrix. I'm not talking about those simulations today, because I'm just talking about semi-supervised with K less than N. Okay, so the amount of bias corrected, and therefore the improved coverage, if I have 2K, depends on the number of basis functions, which basis functions they are, and if I wasn't pretending it was known, how I estimated the covariance. Okay, so there are various ways you could try to estimate the covariance matrix. I'll explain one to you, maybe if we have time as we go. How to not estimate the covariance, how to choose out of some big dictionary which K, slightly less than N basis functions I should take. But everything I'm going to talk about today, you can assume you use some algorithm in the training sample to choose to choose which basis functions I'm actually going to use. So I can treat those as fixed too, though in practice, I want to get good basis functions, but we don't have a good solution to that yet. And that's not the point of today's talk. Okay, let's go on. Okay, so I'm now going to tell you what part of the training sample I'm going to estimate. Okay, that's going to be the key. And then I'm going to show you I have an unbiased estimator of it with my U statistic. So let's take BXI minus B hat XI is the error for person I that you made in estimating the mean of Y given X. And I'm going to regress that in the estimation sample. The training sample is just fixed. It gave me B hat. I'm going to estimate the regression of that on Z of K of XI. But I'm going to think of, for the moment, the population regression. So the population regression, which I'll call beta sub B, because I'm going to do one for the propensity score 2, times Z bar K XI is my predicted, is going to be the projection of the function B minus B hat on those bases. And so the population least squares, so that's what that symbol means. That means the projection, without a hat, it means the population projection of that function on those bases using ordinary least squares, the L2 projection. Okay, and it's, go back, I just want to, and so the projection just uses the population least squares coefficient, which is that, as you all know, which I can, since yi is a conditional on x is an unbiased estimate of b, it's also the expectation, where now everything in that expectation, the inside of it, are empirical things, so I might be able to estimate it. Okay. Okay, go ahead. So I know, okay, so here's what I'm going to, this is the part of the bias I'm going to estimate. It's the projection of the residual b minus b hat on my basis functions times the projection of pi minus pi hat on my basis functions, and I take the mean of that. Okay, so let's now, I'm going to soon talk about how much of the bias is that I just estimated, but this is going to be part of the bias, as I'll show you. So given this is the part of the bias, I'm going to try to estimate what should I use as an estimator. Okay, that's the next question. Well, we saw that you could write the projection b minus b hat as that expression is equal to what I show there. And to see that, if you just substitute in the definitions I gave you of the projection b minus b hat on zk from the other slide, and just look at the algebra, that's what you get, okay? That's just algebra. I defined those things on the other slide, just do the algebra, that's what you get. And I'm going to give you an unbiased estimator of it, given that I know the inverse covariance. And I'm going to use a second order U statistic. Why am I going to use a second order U statistic? Because this is a product of two objects, each of which I have a natural unbiased estimator of. Yi minus b hat xi, zk xi is an unbiased estimator of its mean. So I have an unbiased estimator of that guy. I have the unbiased estimator of this guy with A. And so to unbiasedly estimate the product of things each of which you can have an unbiased estimator of, you have to use U statistics or samples, other kinds of sample splitting. So my estimator is the sum 1 over n times n minus 1, because I'm not symmetrizing, of a kernel, a U statistic kernel, okay? And what is my kernel? A kernel is a function of two people's data. And so it's going to be, for person I, y minus b hat zk, and for the other person, it's going to be zk xj, aj minus its estimated mean. And you can see immediately that the mean of IF22K is an unbiased estimator of the quantity, the part of the bias I'm trying to estimate. So I can actually can estimate part of the bias. Okay, let's go on. So, so let me tell you some properties of this estimator, because they're going to be important. Okay, its standard error of IF22K is generally of order the square root of k over n. Okay, so that means if k is less than n, it's going to be less than 1 over n to the half. So this U statistic actually has a standard error, less than 1 over square root of n. And that's not surprising, because you know U statistics usually have standard errors, variance of 1 over, a second order U statistic of 1 over n squared, thus a standard error of 1 over n, but I'm paying a price for having k basis functions with k increasing with n. That's the k to the half over n. But it's going to be critical that I actually have an unbiased estimator of something whose standard error is less than what you usually think the minimum standard error is, because I'm using a second order U statistic and having k less than n. Okay, because the standard error of my original estimator, that I haven't corrected its bias with IF22 yet, is 1 over the square root of n. Therefore, the standard error of IF22K K is much, much less than the standard error of the original estimator, okay? So that says my partially bias corrected estimators, or my estimator psi2k, where I take my doubly robust estimator and subtract off this new guy, has length approximately equal to the original confidence interval, the walled interval originally centered at psi hat dr, reported in the paper I'm trying to criticize, because I'm adding something whose sampling variability is less than 1 over square root of n. So its sampling variability is not C. Okay, let's go on. That means it's going to be possible to detect for any delta greater than 0 that the absolute value of the ratio of the part of the bias of psi dr that I'm estimating, the mean of IF2 to its standard error exceeds delta, provided the sample size is sufficiently large. So what that means is I'm going to actually be able to tell you, usually we think things that order 1 over the square root of n, I can never have a perfect test between them. But because IF22 has such a small variance, if you give me, bias, the part of the bias of psi hat dk I'm estimating with IF22 is delta over the square root of n. That is, its ratio, the ratio of the bias, the ratio of the bias to its standard error exceeds delta, which means that the bias is some order of 1 over the square root of n, not near 0. I can actually detect, I'm going to be able to detect as n goes to infinity with probability approaching 1, that little bias is there, and I'm going to have incorrect coverage. Okay, so that seems pretty cool. I don't know, the first time you look at it. Okay, so let's go on. So what part of the bias, okay, but I'm only estimating part of the bias. What part am I estimating? Okay, well, let's look at the whole bias. So if you remember, the first line there was the whole bias. I call it C bias theta. That's the conditional bias of theta. 1 gene B and pi is fixed. We saw it was that. I can use the Pythagorean theorem that I can say that's equal to the expected value of the product of the projections of B on Z and pi on Z plus the expected value of the projections on their orthocomplement in L2P. Okay, that's just the Pythagorean theorem. The first part of the bias, I have an unbiased estimator of. We just showed IF22K had was unbiased for the product of projections on ZK. The second part of the bias, I have no control over at all, given I've already, because Z bar K the vector Z bar K per is infinite dimensional. So if I don't assume smoothness, coefficients of higher and higher members of the basis are getting smaller and smaller. I have no control. Maybe, the 10 trillionth coefficient in that projection is suddenly a 3. Okay, and so I have bias of order 1. That's true of any estimator. I mean, this isn't something about our estimator. That's a minimax result. If you put no restrictions on B of X, you can never find it. You can never control the difference between B minus B hat or pi minus pi hat, and therefore you can't control in any way the total bias because you can only estimate a part of it. Okay. Okay, so the bias of my bias-corrected estimator then is just exactly the expected value of, we call it, it's the tail bias, the expected value of the product of the projections on the orthocomplements, which is, I have no control over and could be order 1. Okay, let's go on. So yes, I don't know how long, do you know how long I've been talking? Because I have ways to go. You can shut me up when you want. Okay, so as I said, I can never rule out even the bias of my bias corrected estimator is order 1, much less 1 over n to the half, because I need to have a valid confidence interval. I need the bias to be order 1 over n to the half. I can't ever rule out that it's order 1 because I can't see the tails. No one can. So all I'm going to try to do is empirically tell people who think their assumptions about the tails, say they fall off quickly, their Fourier coefficients fall quickly because they believe these functions are highly differentiable. The best I can do is show them their confidence intervals are wrong. I can never say mine are correct because I can never know the real bias because I can't get to the tail. Okay. But I can tell you the following. So now I'm going to consider the parameter because, okay, so the one reason I use this functional is if I take the special case a equal y, my parameter becomes the denominator of that original expression, the expected conditional variance of a. In that one, I can actually say something more about, okay? Because then I know both pieces of the bias are positive. Because if you go back to the expression, the Pythagorean Theorem slide, you go back a slide, 2 slides, or back, yeah, there. So you can see if b and pi are the same, because I'm using y equals a, then these things are positive. So I know that the part of the bias I haven't estimated is positive. I know the direction of the bias, okay? If b does not equal pi, y is an a, I don't even know the direction of the part of the bias I didn't estimate. You see the difference? That's going to be a critical point, which I'm looking like I won't get to. Okay, so only for when y equals a and therefore b equals pi, or pi is b, can I be guaranteed that the remaining part of the bias is positive, okay? All right, let's go on, back to where we were, keep going. Okay, so that means, where was I? Go back 1 slide. Yeah, so that means that I'm guaranteed my bias corrected estimator, psi hat 2k, remember that was my original estimator, psi hat dr minus my bias correction. We know that has bias, it has that tail bias, I call it the truncation bias, the product of the projections on the ortho complement. And so I know I've decreased the bias because I've estimated correctly, unbiasedly, a positive part of the bias. So I know my estimator is better than the original one, okay? If a equals y. We're going to later talk about what if a is not y, which is the more interesting case. But first you have to understand this case. Okay, so then the previous statements are true not only of the bias, are true of all of the bias, not just the part of the bias, because if I can detect in my part of the bias that if my part of the bias I can estimate, if that is greater than, is order 1 over the square root of n, I can tell you your intervals don't cover because the real bias is even further than that, okay? Because all the biases, the one I'm estimating and the one I can't estimate are both positive. So as soon as I can show you the guy I unbiasedly estimated is of order 1 over the square root of n or greater, I can tell you empirically your confidence intervals didn't cover. So that's the big point. I can't tell you anything about the true bias. That's why I should shut off if I use my parents' social values. But I can tell you if my test of the mean of IF22K, the bias I can estimate, compared to your standard error, is that ratio is greater than some delta, that is, my bias is the same order of your standard error, 1 over the square root of n, that immediately says that you can't have correct coverage. Okay, and that's an empirical fact. I can tell you with certainty you don't have correct coverage. On the other hand, if my test doesn't reject, that is, my test that the ratio of the mean of IF22K to the standard error of the original estimator is greater than delta, doesn't reject, I cannot tell you that your confidence interval is covered correctly. How could I? Because I can't ever know anything about the coverage of any confidence interval because I have no control over the bias because of the tail terms. Okay, so you've now seen that I really can, for someone estimating the expected conditional variance, I can actually look at their data, give me the data, I do my IF22K, I compare it in a test to the size of the standard error of his estimator. If that's bigger than, let's say, a quarter, I say, I can tell you the maximum coverage you could have, because it's just a normal whose standard error is not 0, but whose mean is not 0, but a quarter of the standard error. I can tell you what the coverage of that interval is, the maximum coverage, okay? So that's what I promised you I'd be able to do. I can criticize and tell them they're wrong. If I can't criticize, that is, my test doesn't reject, I can't tell them they're right, because we could be wrong by order 1, not order 1/2, because I don't see the tail. But that's all because I knew the bias I didn't estimate was the same sign as the bias I did. Now, we have to go back to the other problem. Okay, let's go on. Okay. Yeah, so go on. I basically said all that. Okay, I said this. Okay, so what can we say essentially assumption free, given I have that I know the covariance of the ZKs? We can criticize, falsify, and improve. We cannot guarantee correct coverage with interval length decreasing with sample size. I can't say anything positive but to criticize. If A and Y now differ, so I don't know the sign of the bias I left out is the sign of the bias I estimated, I can say even less. And now I have to have a dialogue with the guy who I'm criticizing. This idea of dialogue is somewhat a new idea. It would be nice, well, I think I have maybe 5 minutes. I won't get to everything, but I'll explain the idea. Okay, I'm giving you the results of a simulation study. We don't have enough time that shows this actually works in practice. That somebody reports an interval and I prove using convolutional neural networks to estimate the regression, and I prove, I mean, in the simulation that their coverage is 0 using this method, okay? They really did bad. Okay, let's keep going. That's simulation, we're skipping that. Keep going, keep going. Okay, so now what if the bias I can estimate, the mean of IF22, which is the expected projections, product of the projections on ZK, and the bias I can't, the projections on the ortho complement, may have different signs. Then the bias of my new estimator could be greater than that of my original estimator, because I've corrected for the part of the bias I could estimate, but maybe I was correcting in the wrong direction, because it was correcting this way, but the bias and the rest of it was negative, so I moved in the wrong way. And the bias of the tail I didn't see dominated the bias I could estimate, okay? Because it can be order 1. So okay, that's a logical possibility, not that it happens much, that there's this turnover. What can I do then? Well, I have to have a dialogue. So let's go on, the dialogue. Okay, so imagine the dialogue. Authors report in their paper their 1 minus alpha confidence interval based on their state-of-the-art doubly robust estimator. And they appeal to the original theorem I showed you that they need, that the bias is small o n to the minus 1/2. They say, okay, our coverage is fine, okay? But let's see. Okay, and I'm just doing something else here, but I guess I need to do it. So even when they say that, what does it mean to say, oh, the bias is OP n to the minus a half? That's an asymptotic thing. We don't know at this sample size, unless people are doing finite sample size, even if you believe their smoothness assumptions, they often don't know at the finite sample size what their bias is. They give an asymptotic result. It's OP n to the minus 1/2. We don't want that. We want a lot more than that. We want a lot more than that because we're not going to buy their smoothness assumptions either, or sparsity. So we operationalize this. So they say they're justifying their intervals essentially by saying the bias, C bias, I'm calling C bias to be the mean of IF22. That is the part of the bias I can estimate. Okay. No, I'm sorry. That doesn't have any. C bias is the total bias. Forget it. It's the expected value, no projections. They say that's close to, they believe that's close to the asymptotic limit of 0 under their smoothness sparsity assumptions. However, they fail to quantify or operationalize the last clause. So we go into dialogue, okay? Here's the dialogue. Next slide. Okay. Next slide. Whenever a null hypothesis is defined, as it is in almost every Annals paper and stuff, in terms of an asymptotic rate of convergence in the training sample data, that is the rate of convergence of the estimators B and pi, we ask the authors to specify a positive number, possibly depending on the sample size, and then operationalize their asymptotic null hypothesis as a meaningful finite sample null hypothesis. So they'll say the total bias, that's the total bias, they're hoping it's OP n to the minus 1/2, so they're confident. We make them operationalize it as the bias, the absolute value of the bias over the standard error of their estimator is less than some number, let's say 0.3 or 6, whatever they want. I mean, they're going to have to choose this to operationalize, as you'll see in a moment. But now I have a non-asymptotic hypothesis, okay? And so something I can actually test without hand waving. Okay, go ahead. We'll see. So we mean that when H off, what I'm calling HO op there is rejected, we by convention will declare their hypothesis rejected. Go back to the previous slide. They usually say the hypothesis is NHO, but we're going to test HO for a delta op they give us. And because notice, if HO opt is rejected, then essentially at the samples, that's equivalent, or that's like rejecting their hypothesis. Because remember, the standard error is n to the minus 1/2. So if the bias over the standard error is not less than, let's say, 0.3, then it's not small compared to the standard error. It's not going to 0. So that's how, so we call them an operationalized pair. That's the way people, NHO is how people usually talk. HO is how we talk, and we say NHO is rejected when HO is rejected, okay? Because we have tests of HO, as you'll see. Okay, go ahead. Or sort of tests of HO. Okay, so, and the author's delta off depends on the degree of undercoverage they are willing to tolerate. For example, if 88% is the minimal actual coverage they would tolerate for their nominal 90% two-sided walled confidence interval, then under normality, they would select delta opt equals 0.3 as, don't worry about that function, it's just saying if the ratio of the standard error to the, of the bias to the standard error is 0.3 and is normal, then you get 88% coverage of the 90% interval, okay? It's not close to 0, okay. So how do we proceed? Well, suppose we agree that the implicit or explicit goal in ML estimation was to construct predictors that minimize the conditional mean squared errors of B and P. Okay, in fact, researchers who use squared error, use cross-validation in the training sample, that is just, they're going to do cross-validation within the training sample, we're leaving this sample, are using a squared error loss, or explicitly acknowledging this is their goal. That is, they're going to choose their, like in their method, their tuning parameters by cross-validation using squared error. That has to be their goal. Otherwise, they wouldn't have that loss. That's what that loss, they have to be using that loss functions. So, so then researchers who report a nominal 1 minus alpha confidence interval for the expected conditional covariance when B and pi aren't the same should appeal to Cauchy-Schwarz, the Cauchy-Schwarz null hypothesis, and its operationalized version. Next slide. Okay, so I think that's so describe so the Cauchy-Schwarz bias is, so they have their whole idea is they say, under my assumptions, the Cauchy-Schwarz bias defined there, that's the Cauchy-Schwarz functional, is OP n to the minus 1/2. So their null hypothesis is that Cauchy-Schwarz expression is OP n to the minus 1/2. That's their if that has to be their justification if B does not equal pi, why they think it covers, if they're estimating B hat and P hat by cross-validation using square error loss, which many people are doing, you know, in the training sample. So this is the idea, since you probably want me to finish, is suppose I could prove to them that their Cauchy-Schwarz bias is greater than n to the minus 1/2. I reject the hypothesis, the operationalized version of their Cauchy-Schwarz bias, which is Cauchy-Schwarz bias over the standard error, something order of psi hat dr, because that's 1 over square root of n, is less than delta op. If I can reject their hypothesis empirically that that their Cauchy-Schwarz bias is OP n to the minus 1/2 as operationalized in HO Cauchy-Schwarz, then their justification for saying their interval has correct coverage is gone. If they justified OP n to the minus 1/2 by the fact that if the Cauchy-Schwarz is OP n minus 1/2, then the true bias is n to the minus 1/2 by the Cauchy-Schwarz inequality. So if I can prove to them, I can't prove to them anything about their bias because the signs don't go the right way. But if I can prove the Cauchy-Schwarz bias is not n to the minus 1/2, their justification for saying their coverage fails. So that's all I can do when B and pi are different, A and Y are different. And I can get a valid test to reject the Cauchy-Schwarz bias. And the reason is because essentially, because this Cauchy-Schwarz bias is like a positive functional, like the variance. I know which way the biases go. So all I have to do is, you can see, if I go back to my original test where I did IF22 over the standard error of psi d is less than delta. If that rejects, it's easy to see that the Cauchy-Schwarz bias hypothesis, HOCS, also rejects using the same delta. So the same test I had before, the one I've used just using IF22 because I can only estimate part of the bias, is the expected value of IF22 more than 1 over order 1, actually 1 over the square root of n or bigger. That test, rejecting when B and pi, Y and A are different, cannot actually reject the null hypothesis that the true bias, B minus B hat, pi minus pi hat expectation, is is not n to the minus a half. That is, it over the square root of the standard error is not less than delta. But that is sufficient to reject the Cauchy-Schwarz null hypothesis, HOCS, and thus by H0CS, because that HOCS is operationalizing that. So when I reject Cauchy-Schwarz, remember, rejecting Cauchy-Schwarz does not imply the true total bias, the mean of b minus b hat, pi minus pi hat, is not small, because Cauchy-Schwarz is an upper bound. So I can't say the true bias. All I can tell them is you claimed your intervals covered correctly, because under your smoothness or sparsity conditions, the Cauchy-Schwarz inequalities would be OPN to the minus a half. And I can tell you your justification was wrong, because I can actually test things about the Cauchy-Schwarz hypothesis. It's like the variance is a positive functional, so I know which way the biases are going. In my original test, the IF22 of the expected value of IF22, the estimable part of the bias of the standard error, is less than delta. That test is actually, if it rejects, then you have to reject the Cauchy-Schwarz being less than n to the minus a half. And so the justification is gone. So there's no basis for them to having written down their walled interval, and they just have to empirically admit that. That means also that essentially that I've disproved their sparsity or smoothness assumptions, because they put in enough sparsity and smoothness, they reversed engineered to get the right, to make Cauchy-Schwarz OPN to the minus a half. And I've empirically proved it's not. Now, if I fail to empirically prove it's not, that doesn't mean they have no bias. They still could have bias order 1. All I can hope to do is, if I reject my usual test rejects, I can tell them your justification for your confidence interval fails, because either your sparsity assumptions or whatever assumption you made can't be true, because they imply a small Cauchy-Schwarz OPN to the minus a half. And that I can empirically say is not true if my test rejects. All right, I'm going to leave it there. That's the logic of the whole thing. It's all of this new way of thinking about just criticize, and you have to be in dialogue. You have to see that they base their validity on the example I did on Cauchy-Schwarz of their bias being less than the standard error. Okay, I'm done.
All right. Thank you, Professor Robbins, for the great talk. And maybe let's go over some of the questions. The first one is regarding whether it is possible to develop any lower bound to show optimality of your result.
Okay, as we discussed this a lot, especially with Rajarshi, Maherje is very into this. There's no clear answer to that, because I don't know what you want. Try to define what it is that you want a lower bound for in this setting. Mm-hmm. So the kind of thing we're more interested in is, the big problem here is getting a good choice of basis function z bar k, okay? Because remember, the amount of bias I estimate is the projection of the residual b minus b hat and pi minus pi hat on these z bar k's. So they better be good for explaining those, you know, we want them, those b minus b hat and pi minus, have a big projection on those when b minus b hat and pi minus pi hat are large, when you've got bad estimates. And so the kind of thing we're starting to think about are, therefore we think about oracles. Suppose I told you, so I give you a dictionary of, let's say, you know, has much more greater than n candidates, you know, functions of x, And I want you to pick the k less than n of them. Let's fix k, n over 2 of them that explain the greatest part of the bias. Have the mean of IF22k being the largest. I'm even taking the simple case where we're doing the expected conditional variance, so I'm not worried about signs. So how close can we find an empirical way to choose the bases? How close can we come to an oracle who knows the best approximating bases for k less than equal n over 2 when we have d much greater than n to choose from? We aren't even anywhere close to solving that problem. So that's the fancy problem that seems most important to us by far, because the power you can hope to get is going to depend on how much of the bias you can estimate. You want guys to choose basis functions that explain b minus b hat and pi minus pi hat well. And that turns out not to be such an easy question, because the reason is you're already in small, b minus b hat may already be quite small. Maybe, 10 to the minus, a sixth or something. So it's how to do that and choose it, and what algorithm to use, and how to prove that you're close to the oracle is an open question that we're working on.
Mm-hmm. Thank you. And another question is as follows. So suppose we are in a high-dimensional setting where the number of features is more than the number of data we have. Then there will be some, and we assume that the underlying model is sparse. So in that case, the sparsity assumption seems to incur a bias. So that type of bias affects your result.
So usually, you're worried about if you look at the papers that do the math of that, they usually put in enough assumptions on the sparsity of b and pi such that the rate of convergence they get, b minus b hat and pi minus pi hat. This is not my method. The people who are using the state of the art, they have to estimate, they need b minus b hat times pi minus pi hat to have expectation OP under the minus 1/2. They just put in enough smoothness condition, sparsity conditions to make that happen. So, I mean, and in terms of rates, I don't, in general, under sparsity, I mean, this comes down to the way you're thinking of what estimator are we using. If we're using the lasso, you're asking the question, as far as I can see, just is lasso optimal for estimating the L2 error of a regression function, okay, with random x's, when d is much greater than n. But the sparsity is less than n. And so that's been studied by a lot of people, and if that's not optimal, choose whatever they found to be better. But the point is we let them to start with their best estimate of b hat and p hat they can. Then we do this projection. Our projection is unbiased. We're not, so that's another important thing to understand. We, once we choose k less than n, remember that's the oracle problem I was worried about. Once we choose k less than n, we don't suffer from using an unbiased estimator of the expected value of the product of the projections on CK, because usually the problem with that is you get all this excess variance, right? If you don't regularize. And so you can change a little bias. But for us, because it's a U statistic, the object we're estimating, we're estimating, the mean of IF22, we're estimating at a rate faster than 1 over the square root of n by using an unbiased estimator with no regularization at all. Once we've chosen k less than n. And our view is we don't, if the person's assumptions were right and were sufficient to get n to the minus 1/2, their sparsity assumptions, and they were right, their estimator would be fine, and so would their confidence intervals. We just don't believe their assumptions, because people usually, as I say, reverse engineer their assumptions to make sure that the bias, the expected value, the whole total bias, pi minus pi hat, b minus b hat, is smaller than OPN to the minus 1/2 by showing the Cauchy-Schwarz bound is OPN to the minus 1/2, which depends on the rate they can estimate b and pi under their assumptions. I don't know if I answered at all your question.
Thank you. So another question is regarding on whether it's possible to extend from the binary action setting you just presented to, say, multiple actions or even continuous action set. Whether the algorithm can be directly extended or easily modified to those.
So yeah, it can be easily so the point is, yes, both of those can happen. It's not whether it's, as I said, there's this entire class of functionals. We call them mixed bias property functionals. It's on the archive, or maybe it's out in Biometrica by now. There's a huge number of functionals, 2 of which are the expected conditional variance, the expected conditional covariance, the ones I concentrated on today, because they're so simple to understand. But yes, they're functionals. So the ones we're talking about, yeah, so this is a little complicated. You can have a continuous treatment, but you could have still a functional that has a positive semi-parametric information bound, because you just, because you take some integral of that. But actually, these methods can be used even if your functional doesn't have a positive information bound. But not many people treating problems that don't have positive information bound by leveraging double robustness in the first order, the quotes first order influence functions, because they don't have first order influence functions, but their regularized versions do. You cut the, you cut the number of bases. You use a sieve in some way. And I'm not explaining this well, but the point is there are a bunch of functionals that do have positive information bounds, just the way the expected conditional variance and the special conditional covariance have positive information bounds. Remember, positive information bounds doesn't mean you can achieve those bounds. They just mean you can't do any better. But as we saw, we can never guarantee without assumptions, you can even be within order 1 of the truth, okay, of the expected conditional variance. Those are lower bounds, which are often not achievable. Even if the lower bounds are not as good as n to the minus 1/2, you can still use these methods where you use doubly robust estimators and so forth. So there's some people who are doing this. There are recent papers by Ed Kennedy and Mark Vanderland and some people he's trained that are doing double robustness in the non-root n range. And in our higher order influence papers, we actually do much more complicated robustness. I don't think I'm getting directly to what you want. So let me just say there are lots of other functionals, and a lot of them allow continuous treatments.
Thank you. Maybe
they have a certain structure of the bias called the mixed bias property.
Thank you. So maybe it's the last question. So it's about it's as follows. So suppose the data are not coming at the same time, and we have a stream of data. Say that even the data might be divided into blocks. Then is it possible to, and in the algorithm that you just introduced, you construct a basis which is of dimension k, and k is smaller than n, or a bit smaller than n. Then if the data come into blocks or in streams, is it possible to, say, modify the algorithm to handle the streaming data or the dynamic?
I don't know about that, but I think so, because there's a way to look at streaming data if you use an estimator that's like an average of all the estimators you've made along the way, that is effectively has the same properties as sample splitting, except it uses martingale arguments.
Mm-hmm.
I think, again, Alex Ludke, I mean, the one I know about, and Mark Vanderland, have a paper in the Annals, I think it's in the Annals, about estimating optimal treatment regimes, having nothing to do with what I'm talking about here, essentially, where they leverage that relationship to do essentially what sample splitting would do. In fact, in a certain way, does even a little better. But it's because the new data, you've already done something with the old data, so you can condition on it each time, so it's fixed. And then you use martingale arguments to combine them all. Mm-hmm. So it is like data splitting.
Okay,
the way to do the algorithm. Yeah.
Mm-hmm. Yeah, thank you. It seems I'm running out of the questions, and thank you, Professor Robbins, again for delivering such a great talk. And also thanks everyone for joining today. We are looking forward to seeing you guys next week. Thank you.
Thank you.